So let's talk about differential equations, all right? So why should we care about differential equations? Like, what is the big deal with them? Like, what are they useful for? Well, let's just imagine we have the following situation, okay? I want to figure out I have an object, okay? I have some object, all right? You know, it's like right there, all right? And the idea is that, okay, it's attached to the wall. You know, it's a spring that's attached to. And I'm interested in finding out, okay, where is this object in a given position? So like here is the position 0. Here's the origin right here. And I want to figure out, okay, as it sort of moves around this object, where will it be at any specific time? You know, what is x of t here? All right. So how do we describe this sort of situation? How do we describe the basic physical makeup? Well, you know, this is a physical object right here. This is going to be we're going to be able to apply Newton's laws to it. You know, F equals ma. All right. Force equals mass times acceleration. All right. So what is going on there? Well, on this object right here, basically we have a spring, and that spring is going to do different things as depending on where the position of this guy is. All right. So if he's really close, then the spring is going to be incredibly tight. That's going to push it that way. It's going to feel a force that's positive when it's at this negative value. And when this object is really far out, it's going to feel a force in the opposite direction, like that. Okay? So you see that the force is pointing in a negative direction when we're positive. Okay? And what is the basic way that we describe this force? Well, we describe it this way. That force is equal to negative kx. All right? All right. And so what is going on here? Basically, the idea is k is just some constant for the spring, as in if k is huge, then this spring is really tight. Very reactive to small changes. If k is really small, then it's a very loose spring. You can go all over the place and it doesn't really care. And the negative here is to represent that it's the opposite. And x is basically the position. So basically, the farther out you are. So if I'm right here, I feel a certain force. If I'm twice as far away, I feel twice as big of a force. If I'm 10 times as far out, I feel 10 times as big a force. So that's the basic idea, that the force is equal to some proportion of the position, okay? A negative proportion, all right? All right, now that's fine. Now, what about this side here, mass times acceleration? Well, no mass, that's just basically how heavy this guy is, or basically how heavy he is. But acceleration, what's the way we think about acceleration? We think about acceleration as basically the second derivative of position, right? As in, we all remember that the derivative of position is velocity, the derivative of velocity is acceleration. So therefore, the second derivative of acceleration here, of position, is acceleration, okay? So doing this analysis of what is the force like and what is acceleration, we get the following equation here. Kx equals mx double derivative. That's interesting right there. What we have here is basically we want to find out what x is. We don't know what the function of this object's position is in terms of time, okay? We don't know that. And what we do know about is this relationship, okay? And what is this relationship like? It's a relationship where, okay, this is the function, you multiply it by something, and that equals its second derivative times something, okay? So what's going on here is, hey, that original function of x is related to its derivative in a certain way. It has this sort of relationship here, okay? All right, now let's, I'm just going to shift this a little bit over, okay? I'm going to make this like negative km, let's do x equals x double derivative. Okay. So we have the idea that there's this equation between x and its derivatives. there's some way that derivatives have an equation, we have a differential equation, okay? Now, what does a solution to a differential equation look like, okay? Like what would be like an x of t that would work for that? Like what does it even mean to satisfy a differential equation? I'm not being clear about that, okay? Well, basically the idea, well, let's go back to just regular equations for a second, all right? Let's just have a little reminder, all right? I'll answer this in a second, let's have a little reminder. A regular equation is like you know, x plus 1 equals 2, let's say it's over 3, okay? Here's like a regular equation, regular algebraic equation. How do we know that a certain number satisfies this? Well, basically, it's like, okay, if I put in 7, no, if I put in 3 into there, okay, then what happens, okay, I do this operation right here, 3 replace the x, plus 1 over 3, that gets me, oh, I'm sorry, I got a little confused there. This should be 5. X is over 5. So this turns into 6 over 3. That equals 2. And that's exactly what it should be equaling there. Okay? That's exactly what it should be equaling. Okay? So the idea is, hey, if I plug in a certain number into this equation, it satisfies that equality. Right? I take that certain number, I add 1, divide by 3, I get 2. Alternatively, you know, you have equations that look something like you know, x squared minus 2x plus 1 equals 0, which I could also rewrite as like x squared equals 2x plus 1, minus 1. And the idea is, okay, there's going to be certain numbers that will satisfy this, right? How do I know that certain numbers like 1 and negative 1, just 1. How do I know that 1 satisfies this equation? Well, the answer is, oh, I plug in 1 over here, I get 1. I plug in 1 over here, I get 1. Oh, so both sides, when I replace the x's by 1, gives me 1. Okay? The same sort of logic is going to happen over here, okay? Except, instead of plugging in a number, okay, instead of plugging in 1 into an equation, we're going to plug in an entire function. So with regular algebraic equations, our solutions are numbers. With differential equations, our solutions will be functions. Okay, so that's a lot more complicated. All right, so let's see how it might work out here. Okay, now one good thing with differential equations to understand is that a great method for approaching differential equations is guessing. Okay, and when I say guessing, it's not like totally throwing darts against the wall, but you know, just try out some functions, see what happens, modify as you go. Okay, so you know, I think I'll give out. Let's just try some stuff, see what happens. Okay, so let's just say that I'll rewrite the equation over here. Mx equals x double derivative. Let's say I'm just screwing around, I just try t. Alright? X of t equals t. Let's see what happens when I try that solution. So negative k over m, I place x with t. And over here I place x with t again. Alright? This guy right here turns into negative k over m times t. This guy over here, let's see, the first derivative turns that into 1, and then the second derivative turns that into 0. And we see here that, oh, this function right here, negative k over m times t, does not equal 0, right? As in, this is the function, this is the graph of 0, this is the graph of negative k over m. These guys are different. Maybe at one point, but that's just one point. Okay? Okay, so that failed. That failed because, hey, I plugged that into both sides, it gave me two different solutions. Alright, so what else can I do here? What's another thing? Well, this whole t idea and taking these derivatives, it kind of reminded me of the power rule, sort of. Okay? as in like, oh, you take derivatives and you get a number out afterwards that gets multiplied by. Okay. So let's maybe try that a little bit. Let's do x of t equals t negative k over n. All right. All right. So let's try this guy. Let's see what happens right there. All right. All right. So we plug this guy into this equation here. All right. So we get negative k over m x. We replace the x with t negative k over m. All right. On the other side, we put in this guy where the double derivative is. This just turns into negative k over m, t negative k over m. And this guy over here turns into negative k over m times t negative k over m minus 1, which is kind of seeming like what we want, right? It has the same constant here. I have to take one more derivative though, and that gives me negative k over m minus 1 t negative k over m minus 2. Okay? And we see here that this is wrong. Okay? This t is very different from that t power, and the exponent's very different, and even the constant here is different. Okay? Alright? And you might be thinking that, well, maybe one thing we could do is we could screw around with this to some extent, so that maybe that eventually turns into this constant, you know, some kind of thing that looks like that. But that will not work out because these guys will be different every time. So polynomials, let's not try those. Let's try something else. Let's try x of t equals sine of t. What the hell? What the hell? Alright, so x of t sine of t, let's plug that into there. What does this look like? Negative k over m sine of t. And then on the other side I have sine of t double derivative. Negative k over m sine of t. This guy is negative sine of t. This is not equal, but look how similar this is suddenly. Look how similar these two guys are. I have a sine, it's even negative. It's even negative. That's killer right there. Alright? The only problem is this k over m. The only problem is this k over m. So I think, is there any way I can make like a sign, anything way I can modify a sign such that I can put it, when I derive it, it'll get me out some number that'll eventually turn into that. And I think, well, I know this rule. I remember from the chain rule that, hey, you take the derivative of sine at, that gives me a cosine of at, right? As in I get this constant out, and if the double derivative, that looks like a squared cosine of at, negative sine of t. So, that's great right there. So what I really want this a right here to equal, this a right here, I want that to equal k over m. So what the hell, let's just make this a square root of k over m. Alright. Okay, so that's an idea right there. Let's give it a shot. Let's see where this goes. So let's try this. I'm going to erase this failure over here. So let's shove that in there. Let's do x of t equals sine of square root of k over m t. On one side I get negative k over m sine square root of k over m t. And on the other side I get sine square root of k over m t double derivative. This is just what it is. And then on this other side, what happens is I take the derivative 2 times, I get like negative sine square root of k over m, and then this comes out, gets twice, and I get k over m. All right. So on one side I have negative k over m sine like that, negative sine with a k over m. These two sides are equal. These two sides are equal. So hey, we just figured out that this right here, this sine square root of k over mt, that is the solution to this equation right there. At least that's one of them. Okay. Another one, which you could probably guess, is cosine square root of k over m. See, that's another one that works here. Okay. And there's many other ones, like you can do 4. All right. So we have a whole set of different equations here that could satisfy this differential equation. So sets of different functions here. Okay. Now we're not going to be pursuing equations this complicated at first, but I just wanted to give you the idea of what we'll be doing in this course. We're going to start off with a nice, clear physical problem that makes sense, right? An object vibrating. Okay, which comes up all the time in different places in physics and engineering. Okay, we have this equation which makes sense. We break it down, like what is the force, what is acceleration, and then we get a differential equation. How do we solve this differential equation? We'll find a ton of different techniques to do that, but I wanted to make it feel somewhat natural. Hey, I guessed at one thing, I tried to modify that, I got this guy, and that was sort of better, but again, it wasn't going anywhere. I tried another guy, I'm like, oh, this sounds good. Is there any way I can modify this guy? Yes! Yes, there is a way to modify that. And then it was like, clear, well, if it works for sine, it should definitely work for cosine. Alright, so that is, I want you guys to feel that sine and cosine, that differential equations are not just a magic trick. That it isn't just a series of arbitrary manipulations, that it isn't just a revelation from God, passed down from Mount Sinai. Like this is there's actually a nice, clear, rational process behind it that you guys could reproduce. Okay? Alright, so I think that's enough in way of introduction. Let's get into the first kind of differential equation that we really want to approach here. Okay? The first kind of differential equation, which I'm going to approach, we're going to be using very long and tedious names for this stuff. Let's see. Let's think about this. Do you want to use that name? Yeah, I'll use the name for your notes. I won't talk about the name until later. Linear, first order, homogeneous. Pretty sure I'm misspelling that. Keep it like that. Well, the equations. Okay. Alright. So let's first talk about this, alright? I'm not going to talk about that name because that name is disgusting. We'll talk about that later. Alright. So let's deal with a more familiar differential equation, okay? One that we've kind of maybe seen before a little bit, okay? Let's talk about a population equation here, alright? So, I have a population, all right? And I also make this sort of feel kind of natural, sort of like this makes sense how I'm coming up with the differential equation in the first place. Let's say I have, a population, imagine that's like people, or something like that. And the idea is that here is the population, here's time, all right? And so here's day 0, 1, 2, 3, 4. And the population is, let's make this 10, 20, 30, 40. So these are years right here, okay? And the idea is that, okay, we start off with a population of 100. We then had a population of 110. We then got 121, 132, 145. Okay? Alright. We have this population, and this is the rate of growth right here. Okay? Now I want to be able to predict what's going to happen in the future. Okay? I want to be able to predict, okay, what's going to happen in the next 10 years, next 10 years after that. I want to be able to predict what's going to happen, alright? In maybe like year 50, alright? And beyond, okay? So in order to do that, I have to figure out, okay, well, how is this growing? What is the underlying function giving me these particular demographic data? Okay. All right, well, one thing I can look at to help me out here is to see, like, okay, what's the rate of change here? Or how much does it change per year? Okay, so change of P. All right, so in the first 10 years, because census is taken every 10 years, I believe, I increased by 10, right? 110 minus 100, so 10. Then the next year, I increased by 11. Next year after that, I increased from 121 to 132. Oops, messed up the numbers here. This should be this, and this should be that. This should be 12, and this is 13. Okay? And one thing I'm seeing here, well, I see a couple of things. I see this is getting increasing, and it's increasing at this fixed rate. But it would, if I kept doing this, then it would kind of skip a number eventually. Go to like, from like 16 straight to 18, something like that. Okay, so that's possible. So I'm going to figure out, okay, so what's a way to describe it? Well, another way of describing this is, okay, what's the relation between the population, now change in the population? Oh, well, I can represent that easily. That's going to be P, or change in P, is equal to P over 10. Okay? That's one way to write it. Alright? Okay, so that's good. Now, the thing is, though, is this is a change in P, right, over 10 years, alright? Now, the thing is we don't really deal with changes in general when we're doing calculus, when we're doing math. We usually deal with rates of change, alright? We deal with how much, at what rate are things changing. Like, that's what calculus is all about rates of change. So, what can I do here to incorporate that? Well, let's just divide this equation here by how much we're changing time, okay? I see that, hey, we're always changing time by the same amount, by 10 year intervals here. So then this looks like, okay, this is going to be 1 over 10 divided by 10p. This is going to be 1 over 100p. Okay? So I see here, okay, p, I have this p over t is equal to 100p. Okay, so I know that, okay, so this is sort of the rate of change equals 1/100th of the population, okay? That's how fast we're growing. Now I look at this again, I think, hey, this is a rate of change right here. This is, if I were to sort of make these changes smaller, that basically just means dp over dt, all right? As in, what's the derivative? The derivative of p is equal to 100 over p, all right? And this makes sense for a population to be growing in this kind of fashion, right? As in, if we always know that, it's going to, 1 out of 100 people are going to have a child that year, then this is a good way of representing this, all right? That's not quite the right numbers, but we know that that would make sense. Okay, so where do we go from here? Okay, well, we now have a differential equation describing this situation. Okay, now what's the solution to this guy? Okay, well, I'll just try something out just to see what happens again. I feel like doing that sort of power rule idea I had earlier of like, oh, let's maybe, I know t, if I try to replace t here, let's say p over t, this, what happens with that? Well, again, I try it over here, I replace t, derivative, 100t, I'm going to get out 1 over here, I get t out of 100 there. These two functions do not equal, so this is not a solution, okay? What's another thing I can try? Well, I got a pretty good sense that if I try that, that pt equals t over 1 over 100, that's probably not going to work. I think I'll just show you that it doesn't work here. So I take the derivative on that, 100t negative 99 over 100. That will not equal 100 over t negative 99 over 100. It's kind of close, so it has the same constant, has the same coefficient here, but the function is radically different. Okay, the function is radically different. This has an exponent of negative 99. Oh, excuse me. This has an exponent of 1 over 100. So that's not going to work either. That's not going to fly. All right. Well, let's try exponentials. Let's try exponentials. Let's see what happens there. So, all right, let's just plug that into the equation. So, let me rewrite it over here. P equals 1 over 100 P. With the t's. So let's say P of t is equal to E of t. Well, I end up with E of t derivative 1 over 100 E of t. This right here equals E of t. This equals 1 over 100 E of t. These do not equal, so again that doesn't work, but hey, we're kind of closer here. This feels closer because, yeah, the actually has the opposite problem of this guy. This guy had the problem of, oh, right coefficient, wrong function. This has the problem of wrong coefficient, right function. Okay? So again, I'm thinking, what can I do here to make this work? I think, can I modify this guy? And I think, okay, well, what about chain rule? You know, like if I put in like little t over 100 in there, where does that get me? Et over 100. Well, that gets me the following. Et over 100, take the derivative on that. This turns into 1 over 100. Actually, I'll write it this way. T over 100 derivative et 100, right? Chain rule here. I do the outside stays the same, do an exponential, take the derivative on the inside, and that gives me 1 over 100 et 100. And then on the other side here, it's like, okay, I take 100 of et 100. Those two equal. So we see that, hey, for this guy right here, for et divided by 100, taking the derivative is the same thing as dividing it by 100. That's its relationship to itself there. Its derivative is just 1/100th of itself. Okay? So we see, okay, that solution makes sense right there. And this does make sense as a solution because what that's basically saying is that, oh, as time goes by, this guy's going to get bigger and bigger and bigger. Maybe at a fairly slow rate, but it is growing. Okay, so that also just makes graphical sense right there. Okay, so all right, this is great. This is great. We have a nice, straightforward solution to this problem right here. And if we want to figure out, okay, but we have a problem though. I want to figure out how this particular population grows. Okay, and I got this equation out. But the thing is, this is not the only function that satisfies this equation, okay? Actually, this function right here doesn't satisfy the equation. Because if I look at that, and I see what's the first datum right there, that's basically t equal, we see that, oh, at t equals 0, p, or just, p at t equals 0 equals 100, this guy fails, right? I put in 0 into that guy. I get e to the 0, which is 1, which is not 100. So I need a different solution here. What's the other solution? So I think, okay, well, if that worked, may as well try multiple. That's where the try worked out with the other guy we were working with. So what if I just had like C E T over 100? That's just like a generalized multiple of this guy, okay? Where just C, I can figure, is just some constant like 4 or 5 or pi or whatever. Okay, does this guy work? Well, again, we can see, yes, it does. C T over 100, I take the derivative on that. That turns into C E T over 100 divided by 100. And that is exactly what the differential equation that we want right there. Okay, so basically we know, okay, all of these guys work. All of the guys of this form work. So how can I basically make, but the thing is, this constant we have not nailed down. How do we nail him down? Well, we use this information right there. Okay, how do we use that information? Well, if we know that the population looks something like this, we don't know the multiple, but it looks something like this, as in, it could be this, it could be this, it could be this. I don't know which one it is. These are all multiples of each other, but I don't know which one. How do I nail this down? Well, I can just plug this value in. Okay? So what I'll do is, okay, P0, I know that's equal to 100, and then if I plug in 0 there, I get 0 divided by 100, which is going to be C e to the 0, which is, that's then 1 right there, C times 1, which equals C. And we see here, okay, C equals 100. My solution in this particular problem will be 100 ET over 100, okay? And to solve this particular population problem, I needed two things, all right? I first need this differential equation here. This differential equation in order to figure out sort of the class of functions, right? The class of functions, which, I gave it a couple different tries, and then figure out that the exponential one works. And then I had to nail it down, as in out of all these functions, which one is it? Out of all the different C's this could be, which one is it? I used the initial value, this PT equals 0 equals 100, to solve that. Okay, so that's pretty powerful right there. All right? Okay, so now one thing you might be thinking though is, okay, Ray, like that's all very well and good, but populations don't usually grow at that kind of consistent rate. As in, you've got it out here where like all of the time it's like 1 over 100, but like if you're looking at like, I don't know, like deer, deers, they will reproduce at different rates at different times of the year. In springtime, they're reproducing a lot. In the winter time, they might even be dying off. So how can you handle a situation like that? Well, let's try to imagine it, okay? So in the following situation, I'm just going to have this guy as a reminder. Let's imagine that the rate of change of the population here equals, let's make it negative sine of t, p of t. The reason why I'm doing that is because I want sort of the idea that, okay, you have a deer population. It's like, okay, here's January 1st right here. And here's December 31st. And it's like, okay, during winter time it's decreasing, and then during spring it starts to increase, and then at the summer it's like its peak and it's going down again, something like that, okay? So this is a more realistic model because it takes into account how the population might be affected by what time of year it is here, okay? So the other problem, you might have been scoffing up your sleeves thinking, come on, this is obvious, it's exponential, what are you screwing around here for? Like this is, like everyone knows that exponential is the function that's proportional to itself. Okay, that basically, when you take the derivative of the exponential, you get basically just some multiple of itself. We all know that. But here, this is a very different problem right here. It's not just a multiple of itself, it is a multiple of itself times some other function changing with time. Okay? This is a much more complicated problem. How do we handle it? Okay, how do we handle it? Well, let's just first remember what we did in the last problem just now, okay? P derivative of t equals a p of t. How do we solve that? Well, we have this function e a of t, okay? And what was great about that was, yeah, we take the derivative on this guy, and we get the same thing, the original, then times the derivative of what was inside of there, which was a. Okay? That's how we figured out that problem right there. Okay. So, how might this apply here? How might this apply here? Well, what if we use an exponential again? Because, we want some kind of exponential, but we change what's inside of here. We change what's inside of here. Okay, instead of having AT in here and having it spit out this A, let's have something else. So what the hell, I'm just going to put in negative sine of t. Alright, that seems like a good guess, a good starting point here. Okay, so let's try that. Let's see what happens when I take if I say that this is p of t, what happens when I take the derivative on e negative sine of t here, and yeah, I'll just do that. What happens when I take the derivative? Well, I take the derivative of this guy, and I get the same thing. Alright, right? As in, I got doing the chain rule here, I did the outside of the chain rule, the e part, that gave me the original thing. And then I took the derivative on the inside part here. Okay? So, what's the derivative on the inside part? Well, I'll write it out that way. Sine of t derivative, that equals negative cosine of t e negative sine of t. Which is similar but different, right? As in, what I want here is I want the derivative to equal itself times negative sine of t. Here, I took the derivative, I got myself, but I got the wrong trigonometric function here. It's close, but different. So how do we change this? Let's see, what went wrong here? Well, one thing here is, notice, when I wanted to make this guy work right here, EAT, I did not decide, oh yeah, let's just put in EA. All right, I'm not just going to, I'm going to put in EA, and I'm going to take the derivative, and then I'm going to AEA. That's not how that works. This would actually, without equal, 0, right? What I did instead is, I didn't have A in here, I had the integral of A, namely AT, right? Which is different, which is very different. All right? So, if in this situation, for this situation, the solution was, oh, you see this guy, this A right here? Just put the integral of A into the exponential, and you've got it. Let's try that here. Let's give that a shot. Let's basically put in, let's try out P of t equals E integral of negative sine of t dt. And we know what that is right there. That's E cosine of t. Let's try that guy. What happens with him? Well, if we take the derivative on it, E cosine of t, this looks like, I get again, there's going to be chain rule, this part is like that, E cosine of t, and then I take the derivative on the inside part, cosine of t, and congratulations! We get exactly what we want. So this is the original, and the derivative of this guy is equal to itself times negative sine of t. It satisfies the equation. Okay? So we see here that, hey, this much more complicated situation is solved by basically just take this function right here and just put the integral of it into the exponential. Okay, that's how we did it. And in a sense, it looks identical to this situation right here, where A was a constant. Okay, and you guys can kind of see how if I had a more complicated function here, what this would look like in general. The solution would look something like, oh, you have the equation y derivative of t equals a of t, y of t, where a of t could equal all sorts of things like t, or e of t, or cosine of t, or you know whatever. It could equal all sorts of things here. What? And basically the solution to this guy just is going to be e integral of at, or e big AT. We use a to represent the antiderivative, okay? So, or actually one other thing I should say here is this isn't the only solution. You also have to remember that, oh, when we take this integral right here, we had a plus c right here. And how does c's work here? That turns into EC, EA of t, EC. Let's see. So I have e to some arbitrary power. So basically I just have another number right here. As in if I want to, I can just say, oh, this is just C EAT. Okay? So the solutions for this guy all look like this, which you just remember is integral of AT. Okay, and for all of these guys then, if you want to replace this with t, so if a of t equals t, this just looks like e t squared over 2, or with at equals e of t, this just looks like e of t to the e of t, because, you know. So those would be all the different solutions in those different a's of t's. Okay? So that's really incredible right there. Okay? And how are we able to do this magic right here? How are we able to do that? Well, the reason why is just because of just how important the exponential function is. Just because of how significant that guy is. And let me just properly sort of define him, or at least give him like one way of describing him. The exponential function is the function whose rate of change or derivative, right? The rate of change is the derivative, is proportional to itself. Okay? So what that means, oh, so hey, its rate of change is equal to some multiple of itself. Okay, that's what proportional means. Proportional means some multiple here. Okay? And basically because of this property right here, because when you take the derivative exponential, you get itself times something here, that is going to make it extremely important throughout this entire course. The most important function in this entire course, and this is why we're going to see it again and again and again. And that's why we saw it in this situation right here is, hey, I don't want something that's a portion, that's A, as a constant here. I want something where it's like, oh, okay, the derivative on this guy is some function times the guy itself. Well, I just want the exponential somehow. Because when I take this derivative, I'm going to get itself times something. So the idea there is, okay, I do this, which modifies it a little bit to get me there. Okay? Okay, so that's why the exponential function will be all over the place. Okay, and this, so, and again, let me just say something quickly about how this guy grows here. Because one thing that's always good is to make sure you understand why we're getting the solution. So in this particular situation, why is it that we are getting this solution of e to the cosine t, no, yes, e to the cosine t. So let's think about this. Okay. The reason why is because, hey, e cosine of t, what does that look like? Well, cosine of t, let's remember what that looks like, okay? So here's cosine of t. So this looks like this. All right, what happens when I take the exponential of that guy? Well, when it's at its highest value, I'm here like at e, okay? And then when it's at its lowest value, at -1, I'm all the way down here at 1 over e. So basically, the deer population looks like this, where it's like, okay, it's reached its highest value here, and then it dies out, it reaches its minimum, and then it goes back up, okay? So that's what's going on here. All right, so that makes sense. This equation right here, e cosine of t, really helps us to figure that out. I just want to pause it for a minute.